Chapter 12.4, Limits at Infinity and Limits of Sequences. Our goals are to evaluate limits of functions at infinity and find limits of sequences. So limit at infinity and horizontal asymptotes. So looking at this function here, f of x equals x plus 1 over 2x. Here is that graph. So know that, number one, hopefully we are familiar with, remember that there is a horizontal asymptote at y equals a half given this function. And so notice what is happening to the curve as, first of all, as f of x, as the function approaches negative infinity, it is approaching the 1/2. Now on the right, if f of x is approaching infinity all the way to the right, we notice it's approaching 1/2. Definitions of limits at infinity. If f is a function and L sub 1 and L sub 2 are real numbers, then here are the following statements. These denote the limits at infinity. The first statement is read, the limit of f of x as x approaches negative infinity is L sub 1. And the second is read, the limit of f of x as x approaches infinity is L sub 2. Many of the properties of limits listed in section 12.1 apply to limits at infinity. We're going to use these properties with the limits at infinity below to find more complicated limits. So looking here, if r is a positive real number, then the limit of 1 over x to the r as x approaches infinity equals 0, and that's toward the right. Furthermore, if x raised to the r is defined when x is less than 0, then the limit of 1 over x raised to the r as x approaches negative infinity equals 0, and that's the limit toward the left. So let's try that. Example 1, evaluating a limit at infinity. Find the limit. So the limit as x approaches infinity, we have 4 minus 3 over x squared. Now to kind of think about this a little bit more, now that we have some numbers attached to it, as the numbers get larger and larger, right? X approaches positive infinity, so that's going towards the right. So if we plugged in just say 1, then that's going to be 3 over 1 squared, which is just 3. Now, what if we plugged in 10? 3 over 10 squared, that's going to be 3 over 100. And then what if we did 1,000? 3 over 1,000, that's really small. And so I hope you see that that number is approaching 0. So that is why when you're looking at something like this, the limit as x approaches negative infinity or even positive infinity of 1 over x raised to the r, that number in the bottom is going to get larger and larger, which makes it a smaller and smaller number that approaches 0. So here, let's just evaluate this. This is the limit of 4 minus, this is going to be 0 as x approaches infinity. So we're looking at the answer of just 4. So try this example below, the limit of 2 over x squared as x approaches infinity. So here, I see that the answer is just 0. The graph of a rational function need not have a horizontal asymptote. When it does, however, its left and right horizontal asymptotes must be the same. When evaluating limits at infinity for more complicated rational functions, we're going to divide the numerator and denominator by the highest power of the variable in the denominator. This enables you to evaluate each limit using the limits at infinity. So we're going to try that in example 2. Evaluating limits at infinity. Find the limit as x approaches infinity if it exists for each function. So what this is saying is that we look at the highest power of the variable in the denominator. So that is going to be x squared. Now what we're going to do is we're going to take that x squared and divide it to every single value in the numerator and denominator. So let's first write it as a limit. The limit of negative 2x plus 3 over 3x squared plus 1 as x approaches infinity. So we're going to take that x squared and divide it to every single term. So this is going to be the limit of negative 2x over x squared plus 3 over x squared divided by 3x squared divided by x squared plus 1 over x squared. Then we evaluate each limit at infinity. So looking at and this is as x approaches infinity. So knowing what we did in the previous example, so the limit as of negative 2x over x squared, you know the 1x is going to cancel at the top. So we're really looking at negative 2 over x plus 3 over x squared. And then we have 3x squared over x squared, so that's just 3 plus 1 over x squared. Now remember that as x approaches infinity, these values, this is going to be 0, this is also 0, and this is also 0. So now we're looking at the limit of 0 plus 0 over 3 plus 0 as x approaches infinity. And so this is just going to be 0. It's 0 over 3, which is fine. So the answer is 0. So letter B, we have f of x equals negative 2x squared plus 3 over 3x squared plus 1. So same thing, limit of negative 2x squared plus 3. And then, so this is our highest degree here. So x squared divided by x squared. So very similar to the last problem. But let's see what happens. Okay, so as x approaches infinity. So now we notice that these cancel out, and then this also cancels out, and then this will be, this approaches 0, and this also approaches 0. So now we're looking at what's left here, negative 2 plus 0 over 3 plus 0. So this answer is negative 2 over 3. So one more example. 2x cubed plus 3 over 3x squared plus 1. So the limit of negative 2x cubed plus 3. And then we're still dividing by that x squared. So just using the same one to illustrate some examples. We have 3x squared plus 1, and that's all divided by the same x squared. So notice here we have and as x approaches infinity, we have negative 2x cubed over x squared. And then we know on this one, this is going to be, this changes to 0. This also changes to 0. And this will just be a 3. So now the limit, we are looking at negative 2x, just an x, plus 0 over 3 plus 0. This is what we're looking at. And so what happens as x approaches infinity here? Notice that this value, this x, there's no x in the denominator. So if you put larger and larger x values, notice what happens is that it increases without bound. It's going to get larger and larger and larger. Now, if that happens, it's not approaching anything in particular. So therefore, if it increases without bound, the limit does not exist. So those are 3 examples. So try out these 3 examples down here, and then we'll summarize limits at infinity. So trying this out, letter A, that would be 0. Letter B would be negative 2. And letter C, the limit does not exist. So notice here, when the degree of the numerator is less than the denominator, then it's going to approach 0. When they are equal, notice that it's just the ratio of the leading coefficients. And then when the numerator, the degree of the numerator is larger than the denominator, then the limit does not exist. So here to summarize that a little bit more, in example 2, so I'm just taking the leading terms here. In example 2, observe that when the degree of the numerator is less than the degree of the denominator, as in part A, so the limit of 2x over 3x squared, and there's some other things here, as x approaches infinity, we know that the limit is going to equal 0. Now, if the degrees of the numerator and denominator are equal, then it's the limit is a ratio of the leading coefficients, or the leading term. Sorry, leading coefficients is correct. So negative 2 over 3. Then, when the degree of the numerator is greater than the degree of the denominator, as an example C, then we know that the limit does not exist. Okay, so this is very handy for evaluating limits at infinity for rational functions.